Hello everyone, today we will study areas between curves. How can we find area between two curves? Let f and g be continuous functions on the interval from a to b. Assume f of x is greater than g of x for all x on the interval from a to b. The picture looks like this. Suppose that's a graph y equal to f of x. That's the graph y equal to g of x. Assume f of x is greater than g of x for all x on the interval from a to b. Assume the interval looks like this. Assume that's a, that's b. Here we can see that f of x is greater or equal to g of x for all x on the interval from a to b. Now, how can we find the area between function f and function g? So, in order to find the area between the curves, let me first of all divide AB into n subintervals. Assume that's S1, that's S2, continue, that's x sub I minus 1, that's x sub I, continue, that's the last subinterval, x sub n minus 1, and b is x sub n, a is s sub 0. We try to find the area on each subintervals, and then add them up. We try to find area between the curves on each subintervals, and then add them up. Now, how can we find area on each subintervals? How can we find area on each subintervals? First of all, we can see that here, the area between the curves on each subinterval looks like a rectangle. The area between the curves on each subinterval looks like a rectangle. How can we find area for each rectangles? We know that area of a rectangle is always length times width. On the first subinterval, the width of this rectangle is delta S1. On the second subinterval, the width of this rectangle is delta S2. And continue on the I subinterval, the width of this rectangle is delta Si. And on the last subinterval, the width of this rectangle is delta Sn. Now, that's the width. How can we find the height of each rectangle? How can we find the height of each rectangle? Let's pick typical one. Let me pick typical one here. Consider the i's subinterval. Consider the i's subinterval. How can we find the height of this rectangle? In order to find the height of this rectangle, I choose a sample point between x sub I minus 1 and Si. Let me call this sample point xi star. In order to find the height of this rectangle, I choose a sample point between x sub I minus 1 and x sub I. Call this point xi star. The sample point could be any point on the interval. Let me call this sample point Si star. Once I choose a sample point, I can find a point here on the curve. This is f of Si star. This is g of Si star. Then use the sample point to find the height of the rectangle. Use a sample point to approximate the height of the rectangle. Here, for the height of this rectangle, I can use f of Si star minus g of Si star, since f is larger. So for the height of the rectangle, I use f of Si star minus g of si star. That's the height of this rectangle. Now, for the width of this rectangle, I have delta si here. For the width of this rectangle, it's delta si. That's the width of this rectangle. Width times the height. That's an area of this rectangle. The width times the height. That's an area of this rectangle. Then do the same thing for every rectangle. Do the same thing for every small rectangles. In the first interval, I choose a sample point called S1 star. So that's G of S1 star. Use a sample point to approximate the height. I can find the area of this rectangle. On the second interval, do the same thing. I choose a sample point. Choose a sample point between S1 and S2. Then we call this point S2 star. So this point is F of S2 star. And this point here is G of S2 star. Then use this point to approximate the height of this rectangle. That's an approximate area of the second rectangle. Then do the same thing for the nth rectangle. I choose a sample point between x sub n minus 1 and x sub n. Call the sample point Sn star. So this point here is F of Sn star. This point here is G of Sn star. Use this point to approximate the height of this rectangle. So that's an approximate area of the last rectangle. So then add them up. Then add every rectangle together, and the area of each rectangle together. So I'm taking the sum. For I from 1 to n. That's I equal to 1, I equal to 2, continue until I equal to n. Add them up. This is an approximate area between the curves. This is an approximate area. This is an approximate area between curves. Now, in order to find the actual area between the curves, we must take a limit to make this rectangle very, very small. In order to find the actual area, we must make this rectangle to be very, very small. Make this rectangle to be very, very small. So I take a limit as the maximum delta Si approach to 0. If I take a limit as the maximum delta Si approach to 0, that means every subinterval will be very, very small. If I take a limit as the largest delta Si approach to 0, every subinterval will be very, very, very small. Then the area under the curve will be very, very accurate. That's an actual area under the curve. So everything stays the same. Summation I from 1 to n. F of Si star minus G of Si star times delta Si. What's this? This is a Riemann sum. When we take limit as the maximum delta Si approach to 0, this match the definition of integral. This match the definition of definite integral. So this expression can be written as integral from a to b. Since this match the definition of integral, this expression can be written as integral from a to b. For the function here, I write f of si star as f of x. Write g of si star as g of x. And write delta si as dx. That's an area between the curves. That's an actual area between the curves. That's an actual area between the curves f and g on the interval from a to b. That's an area between the curves f and g between the interval from a to b. This is the actual area between the curves f and g between the interval a and b. So keep this formula in mind. For area between two curves, we use the upper curve minus the lower curve, and then take integral from a to b. For area between curves, take an upper curve. Here f is an upper curve. Minus the lower curve. Here g is the lower curve. Take upper curve minus lower curve, and then take integral from a to b. That's an actual area between curves. Next, let's look at an example. Find the area between the curves y equal to x squared plus 1, y equal to x over 2, x equal to 2, and x equal to 6. In order to find the area between the curves, let's graph these curves first. So first curve, y equal to x squared plus 1. That's a parabola open upward. That's a parabola open upward. Y equal to x squared plus 1. Y equal to x over 2. That's a straight line passing through the origin. That's y equal to x over 2. X equal to 2. That's a vertical line passing through 2 in the x-axis. X equal to 6. That's a vertical line passing through 6 on the x-axis. So that's the region between all four curves. That's the region between all four curves. How can we find the area of this region? In order to find the area of this region, let's draw a little piece. Let's draw a little piece perpendicular to the x-axis. Take this piece as a sample. On this piece, we can see that the upper curve is y equal to x squared plus 1. The lower curve is x over 2. That's an upper curve. Based on this piece, we can see that that's an upper curve. That's a lower curve. So, for area between the curves, the area is integral upper curve minus lower curve. Dx. Then take integral from 2 to 6. Take integral from 2 to 6. That's the setup. Then solve integral. We have x squared plus 1 minus x over 2 dx. Take antiderivative. We have x cubed over 3 plus x minus x squared over 4. Evaluate from 2 to 6. If we plug in 6, 6 to the power 3 is 216. 216 divided by 3 is 72. Plus 6 minus 6 squared is 36. 36 divided by 4 is 9. Then plug in 2. If I plug in 2, 2 to the power 3 is a. I get a over 3 plus 2 minus 2 squared is 4. 4 divided by 4 is 1. Then 72 plus 6 is 78. 78 take away 9, 69. A over 3 plus 2 minus 1. 2 minus 1 is 1. A over 3 plus 1 is 11 over 3. Then common denominator is 3. 3 times 69 is 207 minus 11. That's 196 over 3. That's an area between the curves. Next example. Find the area of the region between two curves, y equal to 10 minus x and y equal to 16 over x. In order to find the area between two curves, let's graph both curves first. First curve is y equal to 10 minus x. That's a straight line. Y-intercept is 10, and the slope is -1. Its graph looks like this. Y-intercept is 10. Slope is -1. That's a graph of the curve y equal to 10 minus x. That's a straight line. The second curve is y equal to 16 over x. That's a hyperbola. Its graph looks like this. That's a graph of this curve, y equal to 16 over x. We are looking for the area of the region between two curves. That's a region between two curves. How can we find the area of this region? In order to find the area of this region, we draw a little strip perpendicular to the x-axis. Based on this strip, we can see that the upper curve is in a straight line. The lower curve is a hyperbola. For area between two curves, we take integral using the upper curve minus the lower curve. Here the upper curve is 10 minus x. Lower curve is 16 over x dx. Now here, what's the upper and lower bound? What's the upper and lower bound? Look at this region here. That's the left bound. That's the right bound. They are both the intersection of these two curves. They are both the intersection of these two curves. In order to find the intersection, we set this equation equal to each other, solve x. In order to find the intersection, I set this equation equal to each other, solve x. So here I set 10 minus x equal to 16 over x. Set this equation equal to each other. Solve the equation for x. For this equation, I can first of all multiply both sides by x. So I get 10x minus x squared equal to 16. Next, I move everything to the left side. I get negative x squared plus 10x minus 16 equal to 0. Next, I can multiply both sides by -1. I get x squared minus 10x plus 16 equal to 0. Then solve the equation by factoring. I get s minus 2 times s minus a. Then solve the equation, s is 2 and s is a. 2 is smaller, a is larger. So 2 must be here, a must be here. So that's the left bound, that's the right bound. 2 is the left bound, a is the right bound. So here, if I put it in the integral, 2 is the lower bound, and a is the upper bound. Next, solve this integral, we can find the area between two curves. This integral can be rewritten as 10 minus x minus 16 times 1 over x dx. Next, we take antiderivative for each term individually. For number 10, the antiderivative is 10x. For x, the antiderivative is x squared over 2. 16 is a constant multiple, we leave it the same. If I take antiderivative for 1 over x, I get ln of absolute value of x. Then evaluate from 2 to a. If I plug in a for x, a times 10 is 80. A squared is 64. 64 over 2 is 32. If I plug in a here, I get 16 times ln of a. Next, plug in 2. If I plug in 2, I get 20. 10 times 2 is 20. Minus 2 squared is 4. 4 over 2 is 2. Minus 16 times ln of 2. Then inside the first parenthesis, 80 minus 32 is 48. Minus 16 times ln of a. What's ln of a? ln of a can be rewritten as ln of 2 cubed. Then by the law of Lagrange, we can put an exponent to the front. I get 3 times ln of 2. So ln of a is the same as 3 times ln of 2. In the second parenthesis, 20 minus 2 is 18, minus 16 times ln of 2. Then we have 48 minus 48 ln of 2, minus 18 plus 16 ln of 2. If we combine like terms, I get 30 minus 32 ln of 2. That's an area between the two curves. That's an area between the two curves. Next example. Find the area of the region between the curves y equal to 6 minus x squared and y equal to absolute value of x. How can we find the area between these two curves? In order to find the area between two curves, let's graph both curves first. First curve is y equal to 6 minus x squared. That's a parabola open downward. That's a parabola open downward. Y-intercept here is 6. So that's the graph of this equation, y equal to 6 minus x squared. The second curve is y equal to absolute value of x. This graph is a V shape. It's a V shape passing through the origin. That's the graph y equal to absolute value of x. We are looking for the area of the region between these two curves. That's an area of the region between these two curves. How can we find this? How can we find this area? So first step, let's draw a strip perpendicular to the x-axis. Based on this strip, we can see that that's an upper curve. That's a lower curve. So the parabola is an upper curve. The V shape is a lower curve. So for area between two curves, we use upper curve minus lower curve. Take integral, use upper curve minus lower curve. Here upper curve is a parabola. 6 minus x squared minus the lower curve, y equal to absolute value of x dx. But what's the upper lower limit here? What's the upper lower limit here? For this region, we can see that this is a left bound. This is a right bound. They are both the intersection of these two curves. They are both the intersection of these two curves. So, in order to find the intersection, we set this equation equal to each other. We have absolute value of x equal to 6 minus x squared. Now, how can we solve this equation? This equation contains absolute value. So let's consider this in two cases. Let's consider this equation in two cases. Case 1, s is greater or equal to 0. Let's consider this in two cases. Case 1, s is greater or equal to 0. If s is greater or equal to 0, that means absolute value of x equal to x itself. So I get s equal to 6 minus s squared. Then solve the equation for x. Let's move everything to the left side. I get s squared plus x minus 6 equal to 0. Solve the equation by factoring. I get x plus 3, x minus 2 equal to 0, which means s equal to negative 3 and s equal to positive 2. In the first case, we assume s is greater or equal to 0, so s cannot be negative 3. This is rejected. There's only one solution. In case 1, there's only one solution, s equal to 2. Case 2, s is less than 0. If s is less than 0, absolute value of x equal to negative x. If x is less than 0, absolute value of x is negative x. I get negative x equal to 6 minus s squared. Then solve the equation for x. I can move everything to the left side. I have s squared minus x minus 6 equal to 0. Then factor. I get x minus 3, s plus 2 equal to 0. Solve the equation, s equal to positive 3, s equal to negative 2. In the second case, s is less than 0, so it cannot be 3. 3 must be rejected. In the second case, s is less than 0, it cannot be 3. So there's only one solution, s equal to negative 2. So if s is greater than 0, it must be 2. If s is less than 0, it must be negative 2. So there are two solutions here. Negative 2 and 2. 0 is here. So negative 2 is a lower bound. Positive 2 is the upper bound. That's the integral. Now, in this integral, since it contains absolute value, we can try to make it a little easier. If you observe this region, you can see that this region is symmetrical over the y-axis. This region is symmetrical over the y-axis. So, if I can find half of an area under the curve, and then multiply by 2, I get the total area under the curve. Which means, if I find an area under the curve from 0 to 2, that's half of an area under the curve. And then I multiply the answer by 2. I get the total area under the curve. So that's the same as 2 times the integral from 0 to 2. 6 minus s squared minus absolute value of x dx. And then solve the integral. For x from 0 to 2, s is positive. When s is positive, absolute value of x is the same as x. When s is positive, absolute value of x is the same as x. So I get 6 minus s squared minus x dx. Then take antiderivative. I get 6x minus s cubed over 3 minus s squared over 2. Evaluate from 0 to 2. If I plug in 2, 6 times 2 is 12, minus 2 cubed is 8, I get 8 over 3. 2 squared is 4, 4 over 2 is 2. If I plug in 0, I get 0, 0, 0, which is 0. Then, inside the parentheses, 12 minus 2 is 10. I get 10 minus 8 over 3. Then find common denominator. 10 can be rewritten as 10 over 1. Multiply top and bottom by 3, I get 30 over 3. 30 over 3 minus 8 over 3 is 22 over 3. Which is 44 over 3. That's an area under the curve. That's area between the curves. Next example. Find the area of the region bounded by the curve s equal to 4 minus y squared and the y-axis. How can we find the area here? In order to find the area, let's graph the region first. This region is bounded by the curve s equal to 4 minus y squared and the y-axis. This equation, x minus x equal to 4 minus y squared. This is a parabola. This graph is a parabola. We know that there are 4 different types of parabolas. Y equal to s squared. It's a parabola open upward. Y equal to negative s squared. Y equal to negative s squared. That's a parabola open downward. S equal to y squared. That's a parabola open to the left. And s equal to negative y squared. That's a parabola open to the right. There are 4 types of parabolas. So here all we have is 4x equal to 4 minus y squared. Since y squared is negative, that's a parabola open to the left. Since y squared is negative, that's a parabola open to the left. Now, for this parabola, if I set s equal to 0, y is positive negative 2. If I set s equal to 0, y is positive negative 2. If I set y equal to 0, s is positive 4. And that's a parabola open left. So the curve looks like this. It's a parabola open left. It looks like this. The curve looks like this. That's a parabola. S equal to 4 minus y squared. That's the y-axis. This is the y-axis. This is the y-axis. So we are looking for the area of the region bounded by the curve, by the parabola, and the y-axis. That's the region bounded by the parabola and the y-axis. We try to find the area of this region. How can we find area of this region? Let's first of all draw a strip perpendicular to the x-axis. On this strip, you can see that the upper curve and the lower curve, upper curve and lower curve are exactly the same curve. The upper curve and lower curve are exactly the same curve. If they are the same curve, how can we find area? So let's first of all try to write y as a function of x. For this parabola, let's first of all try to write y as a function of x. We have s equal to 4 minus y squared. If we solve the equation for y, I have y squared equal to 4 minus s squared. Then, in order to get y by itself, I take square root on both sides. I get plus or minus square root of 4 minus x. In order to get y by itself, I take square root on both sides. When I take square root, I get plus or minus sign. Which means the upper curve, the curve above x-axis, is y equal to square root of 4 minus x. And the curve below x-axis is y equal to negative square root of 4 minus x. So that's the upper curve. That's the lower curve. For area between two curves, we use upper curve minus lower curve. So that's very, very special. That's a very, very special case. Both upper curve and lower curve depends on the same function. Both upper curve and lower curve come from the same equation. So here, we use an upper curve minus lower curve. We get square root of 4 minus x minus negative square root of 4 minus x. dx. Then that's the left bound. That's the right bound. Left bound is 0, right bound is 4. The integral from 0 to 4. Simplify. Double negative here is positive. We get square root of 4 minus x plus square root of 4 minus x. That's 2 square root of 4 minus x dx. How can we take integral here? Here we can make u substitution. The u be 4 minus x. Then du will be negative dx. We have a dx here. What's missing is negative sign. That's not a big problem. I can multiply both sides by negative 1. I get negative du equal to dx. Then substitute. I get 2 square root of u times negative du. And then for the upper and lower bound, we plug in 4 for x and plug in 0 for x. If I plug in 4 for x, 4 minus 4 is 0. If I plug in 0 for x, 4 minus 0 is 4. This integral can be rewritten as negative 2 integral from 4 to 0. Square root of u is u to the half du. I pull out negative sign, pull out number 2. Square root of u is u to the half. Then take antiderivative. I get u raised to 3 half over 3 half. Evaluate from 4 to 0. Then when we have a function divided by a fraction, it's the same as saying the function multiplied by the reciprocal of the denominator. That's negative 2 times 2 over 3 times u to the 3 half. Evaluate from 4 to 0. Negative 2 times 2 over 3 is negative 4 over 3. If I plug in 0, I get 0. If I plug in 4 for u, I get 4 raised to 3 over 2. 4 raised to 3 over 2 is a. Together is 32 over 3. That's an area of the region bounded by the parabola and the y-axis. It doesn't look too easy. Is there an easier way? It doesn't look too simple. It doesn't look simple here. Is there an easier way to find area? Now, let me draw a region over and think of an easier way. Instead of measuring area from bottom to top, or if we measure area from left to right, if we draw a horizontal strip, we can clearly see that this is the left side curve, that's the right side curve. The area is bounded by this straight line and its parabola. Left side curve is the y-axis. That can be written as s equal to 0. Right side curve is s equal to 4 minus y squared. Or if we measure area from left to right, what do we get? If we measure area from left to right, we also find the area by taking integrals using the right side curve minus the left side curve. F of y minus g of y dy. If we measure area from left to right, we must write x as a function of y. So that's f of x, that's f of y, that's g of y. We use f of y minus g of y times and take antiderivative with respect to y. Evaluate from the lower bound to the upper bound. The proof is very, very similar as the previous formula. We write x in terms of y, then use right side curve minus left side curve, and then take integral with respect to y from lower bound to the upper bound. Now here, what's the lower bound, what's the upper bound? Here, lower bound and upper bound, they are both the intersection of these two curves. In order to find the lower bound and upper bound, I set these two equations equal to each other. I set 0 equal to 4 minus y squared. Then solve the equation for y. I get y squared equal to 4, y equal to plus or minus 2. So that's the lower bound, that's the upper bound. So the area is the integral from -2 to 2. Use right side curve minus left side curve. Right side curve here is 4 minus y squared. Left side curve is 0. Then take antiderivative with respect to y. Take integral. If I simplify, I get 4 minus y squared dy. If I take antiderivative, I get 4y minus y cubed over 3. Evaluate from -2 to 2. If I plug in 2, I get a minus a over 3. If I plug in -2, I get -a minus -a over 3. Then simplify, I get 16 over 3 minus -16 over 3. Together is 32 over 3. We get exactly the same area. But solving this integral is much easier than solving this integral. So that's another way to find integrals. We can find area from left to right or bottom to top. It's the same thing. We can use upper curve, right side curve minus left side curve. Right side curve minus left side curve. We draw horizontal strip. Decide what's the left side curve, what's the right side curve. Then use right side curve minus left side curve. Use right side curve minus left side curve. Write both curves in terms of y. For both curves, write x in terms of y. Then use right side curve minus left side curve. Take antiderivative with respect to y. So that's another way to find areas. We can measure area from left to right. Next example. Find the area of the region bounded by curves s equal to 4 minus y squared and y equal to s plus 2. In order to find the area, let's graph the region first. First curve is s equal to 4 minus s squared. That's a parabola open to the left. Since y squared is negative, that's a parabola open to the left. If I plug in 0 for y, s is 4. If I plug in 0 for x, y is plus or minus 2. And that's a parabola open to the left. It looks like this. That's the first curve, s equal to 4 minus y squared. The second curve is y equal to s plus 2. That's a straight line. Y-intercept is 2, slope is 1. That's the second curve, y equal to s plus 2. That's the region between two curves. That's the region between two curves. We want to find the area of this region. So there are two ways to find the area. We can either measure an area from bottom to top or from left to right. Now, which way is better? If we try to measure an area from bottom to top, let's draw some vertical strip. We can see that in this region, the straight line is the upper curve, the parabola is the lower curve. But in this region here, the parabola is both the upper curve and the lower curve, which means if we try to measure an area from bottom to top, we must take two integrals. First integral for this region, another integral for this region. It may be too much work. But if we measure, can we measure the area from left to right? Can we measure the area from left to right? If we measure this area from left to right, let's draw a horizontal strip. We can see that no matter where I draw the horizontal strip, the straight line is always a left side curve. The parabola is always a right side curve. So this way is easier than the other way. So measure area from left to right is easier than measure area from bottom to top. In this case, in this problem, measure area from left to right is easier than measure area from bottom to top. Now here, let's measure area from left to right. If we try to measure area from left to right, for both equations, we must write x as a function of y. If we measure area from bottom to top, write y in terms of x. If we measure area from left to right, write x as a function of y. So for this parabola, we already have x as a function of y. For the straight line here, try to write x as a function of y. We have y equal to s plus 2. If I try to get s by itself, I have s equal to y minus 2. So for the straight line, write x as a function of y. Then for the area between two curves, we use right side curve minus left side curve. Here, right side curve is the parabola 4 minus y squared. The left side curve is a straight line, s equal to y minus 2. Then take antiderivative with respect to y. What's the upper and lower bound? What's the upper bound and lower bound? We set these two equations equal to each other. We can find intersections. The boundary here occurs in the intersection. We set these two equations equal to each other. We set 4 minus s squared equal to y. We set 4 minus y squared equal to y minus 2. Then solve an equation for y. So for the upper bound and lower bound, we set these two equations equal to each other. We set 4 minus y squared equal to y minus 2. Then solve the equation for y. I can move y over, move negative 2 over. I get negative y squared minus y plus 6 equal to 0. Next, I can multiply both sides by negative 1. I get y squared plus y minus 6 equal to 0. Then solve the equation by factoring. I get y plus 3 times y minus 2 equal to 0. Solve the equation, y equal to negative 3 and y equal to positive 2. So negative 3 is the lower bound, positive 2 is the upper bound. This is negative 3 here. Positive 2 is here. So that's a lower bound, that's an upper bound. Then solve integral. Let's combine like term first. Inside the bracket, let's combine like term first. I get negative y squared minus y plus 6 dy. Then take antiderivative with respect to y. I get negative y cubed over 3 minus y squared over 2 plus 6y. Evaluate from negative 3 to 2. If I plug in 2, I get negative a over 3 minus 2 squared is 4. 4 over 2 is 2. Plus 12. If I plug in negative 3, negative 3 cubed is negative 27. Negative is positive. I get 27 over 3, which is 9. Negative 3 squared is positive 9. I get 9 over 2. Negative sign stays the same. 6 times negative 3 is negative 18. Then simplify. We get negative 8 over 3 plus 10. 9 minus 18 is negative 9. I get negative. Double negative is positive. I get positive 9 plus 9 over 2. Add the whole number first. 10 plus 9 is 19. Then add the fractions. 8 over 3 and 9 over 2. The common denominator is 6. 8 over 3 is the same as 16 over 6. 9 over 2 is the same as 27 over 3. 27 over 6. It's 19 plus 11 over 6. Then adding up. Here, 6 times 19 is 114. Plus 11 over 6. That's 125 over 6. That's an area of this region. So here, finding area from, in this particular problem, finding area from left to right is easier than finding area from bottom to top. Next example, find area of the region bounded by the curves y equal to square root of x plus 2y equal to 0, and 3x minus 2y equal to a. In order to find the area of this region, let's graph these curves first. First curve is y equal to square root of x. Its graph looks like this. Second graph is x plus 2y equal to 0. For this equation, if I get y by itself, it can be written as 2y equal to negative x, y equal to negative half of x. That's a straight line. Y-intercept is 0. Slope is negative half. So that's the curve. X plus 2y equal to 0. The other curve is 3x minus 2y equal to a. For 3x minus 2y equal to a, if I solve an equation for y, I get negative 2y equal to negative 3x plus a. Then if I divide both sides by negative 2, I get y equal to 3 over 2x minus 4. The y-intercept is negative 4. Slope is 3 over 2. So the graph looks like this. That's the curve. 3x minus 2y equal to a. And that's the region bounded by all three curves. That's the region bounded by all three curves. Now, how can we find the area? For this region, we can either find area from bottom to top or from left to right. If we measure the area from bottom to top of this region here, that's a lower curve. That's a lower curve. That's an upper curve. On this region here, this is a lower curve. This is the upper curve. Since in two different regions with different upper and lower curve, if we find an area from bottom to top, we must cut into two regions. If we find an area from bottom to top, we must cut into two regions. Because in this region, that's a lower curve, that's an upper curve. And in this region, that's a lower curve. That's an upper curve. Now, what if we find an area from left to right? If we find an area from left to right, in this region here, that's the left side curve. That's the right side curve. But in this region here, in this region below x-axis, that's the left side curve. That's the right side curve. Same thing. In different regions, we have two different left side and right side curve. We must also cut into two regions. So there's no difference. There's no big difference. Let's find an area from bottom to top. There's no big difference if we find an area from bottom to top or left to right. In both cases, we must cut into two regions. So here, let's find an area from bottom to top. I cut it into two regions. Let's call it region A1. Call it region A2. Area of region 1. That's an upper curve. That's a lower curve. Since we try to measure area from bottom to top, write y in terms of x. So the upper curve is y equal to square root of x. Lower curve is y equal to negative half of x. That's an upper curve. That's a lower curve. Square root of x minus negative half of x dx. Now what's the upper and lower bound here? This is a lower bound. It's 0. This point here is an upper bound. For A1, that's the upper bound. What's this point? This point is the intersection between this equation and this equation, between these two curves. So we try to set these two equations equal to each other. 3 over 2x minus 4 equal to negative half of x. Then solve the equation for x. I can first of all multiply both sides by 2. Make it a little easier. I can first of all multiply both sides by 2. I get 3x minus a equal to negative x. Then add x to both sides. I get 4x minus a equal to 0. Then 4x equal to a. S equal to 2. At this point, s is 2. So that's the upper bound. That's lower bound for A1. That's the lower bound. That's upper bound. Then solve integral. I get square root of x. That's x raised to half. Minus minus means plus. Half of x dx. Then take antiderivative. I get x raised to 3 half over 3 half plus half of s squared over 2. Evaluate from 0 to 2. Let me simplify first and then plug in. Let me simplify first, then plug in the limits. If I simplify first, I get 2 over 3 x raised to 3 over 2 plus 1 over 4 s squared. Evaluate from 0 to 2. If I plug in 2, I get 2 over 3 times 2 to the power of 3 over 2 plus 2 squared is 4. 4 times 1 over 4 is 1. Continue. 2 raised to 3 over 2 is 2 square root of 2. If we multiply, we get 4 over 3 square root of 2 plus 1. That's the area of region 1, A1. Next, let's find the area for A2. For A2, the parabola square root of x is also the upper curve. Square root of x is still an upper curve. The lower curve is this straight line. This line is 3x minus 2y equal to a. Since we measure area from bottom to top, I must write y in terms of x. Here y is 3 over 2x minus 4. That's a lower curve. So I get square root of x minus 3 over 2 x minus 4 dx. For a2, 2 is a lower bound. What's the upper bound? What's the upper bound here? For the upper bound here, this point is the intersection of between the parabola and this curve. 3 minus 2y equal to a. So in order to find this point, I set this equation equal to this equation, and then solve for x. So I set square root of x equal to 3 over 2 of x minus 4. I can first of all multiply both sides by 2. I get 2 square root of x equal to 3x minus a. Then I can square both sides. If I square both sides, I get 4x equal to 3x minus a squared. Expand left side. I get 9x squared minus 3 times a is 24. 24 times 2 is 48x plus 64. Then subtract 4x from both sides. I get 9x squared minus 52x plus 64. Next, we can factor this using the AC method. X squared can be factored as 9x times x. We try to factor 64, making the outer plus inner equal to negative 54, equal to negative 52. Here, let's try 16 and 4. 9 times 4 is 36, plus 16 is 52. So let's make negative 16 and negative 4. The outer is negative 36x. The inner is negative 16x. Together is negative 52x. Then solve both equations individually. I get s equal to 16 over 9 and s equal to 4. But there's only one solution here. There's only one solution here. Which one is the solution? Which one is the solution? Let's check. If we plug in 16 over 9 for x, I get square root of 16 over 9 equal to 3 over 2 times 16 over 9 minus 4. Square root of 16 over 9 is 4 over 3. 3 over 2 times 16 over 9, if we simplify, we get 3 on the bottom. That's a on the top. We get a over 3 minus 4. Is this true? Four can be rewritten as 12 over 3. A over 3 minus 12 over 3 is negative 4 over 3. They are not the same. So this answer must be rejected. This answer must be rejected. Let's just make sure. Let's check 4. Make sure 4 works. If we plug in 4 into this equation, we get square root of 4 equal to 3 over 2 times 4 minus 4. That 4 works. Square root of 4 is 2. 3 over 2 times 4 is 6. 6 minus 4 is 2. So it works. Number 4 works. 16 over 9 doesn't work. So if an equation contains square root, we must always check the answer. If the equation contains square root, we must always check the answer. So the solution is s equal to 4. And the solution is s equal to 4. So that's the upper bound. 2 is the lower bound for A2. 2 is the lower bound, and 4 is the upper bound. Two is the lower bound, and 4 is the upper bound. Then let's simplify the inside first. I get square root of x can be rewritten as x raised to a half minus 3 over 2x plus 4 dx. Then take antiderivative with respect to x. I get x raised to 3 over 2 over 3 over 2 minus 3 over 2 times x squared over 2 plus 4x. Evaluate from 2 to 4. Let's simplify first and then plug in. If we simplify first, we get 2 over 3 times x to the 3 over 2 minus 3 over 4 x squared plus 4x. Evaluate from 2 to 4. If we plug in 4, we get 2 over 3 times 4 to the 3 half minus 3 over 4 times 4 squared is 16 plus 16. 4 times 4 is 16. If we plug in 2, I get 2 over 3 times 2 to the 3 half minus 3 over 4 times 2 squared is 4 plus 4 times 2, which is a. Simplify. 4 raised to 3 over 2 is a. 2 over 3 times a is 16 over 3. 16 divided by 4 is 4. 4 times 3 is 12. I get negative 12 here. Plus 16 minus 2 over 3 times 2 raised to 3 over 2. 2 raised to 3 over 2 is 2 square root of 2. If we multiply, we get 4 over 3 square root of 2. For the second term, if we multiply, 4 cancels 4. If I distribute negative sign, it becomes positive 3. For the third term, if I distribute negative sign, it becomes negative a. Then combine like terms. Negative 12. Let's do the whole number first. Negative 12 plus 16 is 4. 4 plus 3 is 7. 7 minus 8 is negative 1. Minus 4 over 3 square root of 2. 16 over 3 minus 1 is 13 over 3. Minus 4 over 3 square root of 2. Then for the final answer, for the total area, we take A1 plus A2. This is A1. Take A1 plus A2. We have 4 over 3 times square root of 2 plus 1. Plus A2, this is A2. 13 over 3 minus 4 over 3 square root of 2. Then 4 over 3 square root of 2 can cancel. What's left is 1 plus 13 over 3. That's 16 over 3. That's the total area. That's the area of this region.